Hi class, so today we're going to talk about what are called dominant strategies and their counterpart, dominated strategies. So often when we analyze games, it can be valuable to think about what decisions will our opponent make and what are our best decisions if they make those decisions. So let's take a look at the example from yesterday's worksheet. Remember, player 1 was choosing a cuisine, and player 2 was choosing a location, and we wrote down in this game matrix below how much each person liked each restaurant. This definitely seems like an interesting game, but let's be player 1 for a second and think about what our best strategy might be. Certainly, we want to try to get this valuable 6 payout there, and so, well, what can we do to get that? Well, maybe we'll just choose Mexican. But if that's the case, then we can end up with this 3 payout over there if player 2 chooses to be on campus. Then again, will player 2 choose to be on campus or not? Let's compare player 2's payouts for downtown versus on campus. Now, if they choose downtown, they could get payouts of 5, 3, and 6. And if they choose on campus, they can get payouts of 4, 2, and 5. Which column are they more likely to choose? Well, if you notice, all of the entries in downtown are better than their corresponding entries on campus. Maybe that's not a surprise. But if we notice that, then it only makes sense that player 2 will choose downtown. Why is that? Well, in any of these cases, they choose downtown. If they choose on campus, they would have been better served to be choosing downtown, right? If we choose Italian, then they wish they had chosen downtown instead of on campus. We choose Mexican, they wish that they had chosen downtown versus on campus. If we choose Indian, then again, they wish they were downtown versus on campus. So what we say is that downtown is a dominant strategy, and on campus is a dominated strategy. All we're noticing is that if we choose downtown, it's always better, given each of player 1's choices, than the payoffs for on campus. And so we can sort of eliminate them choosing on campus since it's a dominated strategy. Now, since we know that they're going to be choosing downtown, well, which of our 3 payoffs would we prefer in that column, 3, 6, or 2? Well, we'd prefer that 6, and so we should choose Mexican. So here, Italian is now dominated by Mexican, and Indian is now dominated by Mexican. So by successively eliminating dominated strategies, we can arrive at what we'll call a solution to the game. All this is saying is that it makes logical sense for this to play out that way. The end result will be that we go to downtown Mexican because we were able to eliminate them choosing on campus, and thus, out of our 3 downtown choices, we chose the best one, which was Mexican. One thing that I want to point out is that our strategy of Mexican over Italian was not always dominant. Let's take a look at player 1's 3 strategies. We could do Italian, Mexican, and Indian. And our payouts would be 3, 4, 6, 3, and 2, 3. And now we're choosing the rows. So which rows are better than which other rows? If we compare Mexican to Indian, both of the Mexican restaurants are preferred to both of the Indian restaurants. Okay, we're tied over here 3-3, but we're going to be as satisfied at that Mexican restaurant as we will be at that Indian restaurant. So in this example, choosing to go for Indian food is a dominated strategy. We might as well go for Mexican food. But if we look for Mexican versus Italian, the Mexican restaurant downtown we like better, but the Italian restaurant on campus we like better. So which one should we choose? Well, it's a toss-up. It really depends on what they're going to do. Are they going to choose to go downtown, or are they going to choose to go on campus? Well, from what we said before, the on-campus places are all less preferable for player 2 than the downtown places, and thus we're only going to be choosing between the 2 downtown restaurants, and so we're going to end up, again, eliminating the Italian restaurant and choosing the Mexican downtown restaurant. So sometimes strategies are only dominated once we take into account the other player's dominated or dominant strategies. There's another curious happening in this example. Let's back up to this point here. Now notice that even though downtown dominates on campus, the payout of the on-campus Italian restaurant is better than the payout for the downtown Mexican restaurant for player 2. So out of these 4 choices, player 2 would like to go on campus at the Italian restaurant. So they could try to trick player 1 by actually choosing the on-campus location, even though it's dominated, but then they risk the chance that player 1 might actually choose Mexican, and then they'd actually end up with their lowest score too. Then again, if player 1 thinks that they might switch to on-campus, well, then they actually prefer that 4 over the 3, so maybe they'll actually go for the Italian restaurant. So there's still a little bit of back and forth in this game. The idea of successively eliminating dominated strategies is still a good idea, and it's a logical solution to the game, but nevertheless, there is still a slight back and forth that can happen between the 2 players of this game. You'll recall that the downtown Mexican restaurant was actually a Nash equilibrium point. If you have a Nash equilibrium point and you successively eliminate dominated strategies, you will eventually lead to one of the Nash equilibrium points. Now let's see how successfully eliminating strategies, dominated strategies, can be applied to real-world decision-making. So I have the following example for you. We have 2 gas stations, and they each buy their gas for 20 cents a gallon. Maybe not terribly realistic, although nowadays closer to realistic. And they're on the same stretch of highway, they're on the same stretch of road, so their total volume of cars buying gas a day will combine to be 1,000 gallons. And so the gasoline stations are trying to figure out what they should price their gasoline at in order to capture most of the market and also to maximize profits. So if they sell at the same price, they'll completely split the customers. But if one sells at a cheaper price than the other, then they'll steal all the customers. Okay, so let's fill in this chart. These are their selling strategies. They can either sell for 25 cents, 24, 23, 22, or 21 cents. And both gas stations are deciding between these prices. Now let's start out with 25 cents. So suppose they both sell their gas at 25 cents a gallon. Well, then they'll split the total 1,000 gallons to be 500 each. And how much of a profit are they going to make? They'll make a 5-cent profit. And so how much money are they going to make? 500 times 5 cents. This is just $25. Okay, so here they're both going to make $25. But what's going to happen if gas station 2 actually sells their gas for 24 cents, while gas station 1 sells it for 25 cents. Well then, gas station 2 will get all 1,000 gallons, but they'll make only a 4-cent profit instead, but that's going to be a $40 net profit. And gas station 1, well, they don't have any gas to sell. They would have made 5 cents per gallon, but they're going to have a payout of 0. So the payout to gas station 1 is 0, payout to gas station 2 is 40. And what if gas station 2 does 23 cents instead? Well, then they're only making 3 cents a gallon, so it's going to be $30 of profit. Likewise, 2 cents a gallon will give them $20 of profit, and 21 cents per gallon will give them $10 of profit. Okay. The same thing will happen if gas station number 1 lowers their prices with gas station number 2 keeping their price at 25 cents. Except for these numbers will be flipped. Gas station 1 will not make the profit. 40, 30, 0, 20, 0, 10, 0. Okay, what if they both change their prices to be 24 cents, right? They have an inkling that the other gas station is going to open up with a 24 cents a gallon price tag, and so they think to themselves, aha, I should match them. I will also sell for 20 cents a gallon. Well, then they're going to split how many gallons they sell. Now, since they're both selling at 24 cents, they're only going to make 4 cents of profit, and so they'll make $20 each. However, again, if gas station 2 goes to 23 cents a gallon, they'll still capture the entire market, but now they'll make 3 cents of profit, and so they'll make $30. 0, 30, 0, 20, 0, 10. Same with the other one. Okay, likewise, if they both go to 23, then they'll both make $15. But if one undercuts, they'll get that whole share. They both sell at 22, they'll both only make $10. Again, if one of them undercuts the other, then they'll take the whole share. If they both sell at 21 cents, then they'll both only make $5 of profit. Okay, and so let's think about what is the best strategy for both gas stations. Well, let's compare row 1 to row 2. And let's think about which row would gas station number 1 prefer to be in. Well, 40 is definitely bigger than 25. 20 is definitely bigger than 0. And in all these other cases, they're going to be tied. They're making $0 profit in each case. Well, okay, it looks like selling their gas for 25 cents a gallon is completely dominated by selling their gas for 24 cents a gallon. Now, are there any other dominated strategies for gas station number 1 right now? Well, let's see. 30 is actually less than 40, so they wouldn't prefer to switch to 23 now. 30 is bigger than 20 there, and 15 is bigger than 0 there, and here again we're tied. So if you look, 23 cents does not dominate 24 cents, because if gas station 2 is selling at 25 cents a gallon, then you of course want to be selling at the highest price you can and still capture all the market. So that selling at 24 cents is better versus 25 cents than selling at 23 cents. Okay, so there's no other dominated strategies for gas station number 1. So great, seems like they should sell at 24 cents, right? Well, hold on. Let's take a look at what gas station 2 looks and sees in this table. They realize that gas station 1 is not going to sell at 25 cents because that's a dominated strategy. Now they compare all their options. Well, 20 is bigger than 0. 0 is the same as 0. 0 is the same as 0. And so for gas station 2, now they're like, aha, 25 cents, selling at 25 cents per gallon is just going to lose me all my customers, so I should sell at 24 cents per gallon as well. that is a dominating strategy. That's a dominant strategy, and it's making 25 cents a dominated strategy. So now I can rule out ever selling at 25 cents. Okay. Well, what's going to happen now that gas station 1 realizes gas station 2 won't sell at 25 cents, that they're going to sell at 24 cents themselves? Well, this idea of capturing the entire market and selling at just undercutting the opponent now leads them to make the same choice to no longer sell at 24 cents, but to sell at 23 cents instead. So here, 23 cents, we eliminated that one square that made it more profitable to sell at 24 cents than 23 cents, because we can infer that gas station 2 will no longer sell at 25 cents. And now, row 2 is dominated by row 3. And you can sort of catch on to what's going to happen. Gas station 2 makes the same conclusion after 24 cents is no longer on the table by gas station 1. And so if you look, their column of 23 cents dominates their column of 24 cents. Now that makes the row of 22 cents dominate the row for 23 cents, so on and so forth. Until finally, they both settle on selling at 21 cents each, making only a single cent of profit per gallon sold, and minimizing both of their profits. This idea is the heart of capitalism in the free market system, the idea that competition between two gas stations or two businesses will drive prices down because they realize they can capture a larger share of the market by having cheaper prices. And thus, the consumer is benefited because the consumer gets to pay the cheapest prices possible, and the businesses are able to cover their expenses by still making a profit, albeit a small profit. What's so curious about this is that if you look in this situation, if gas station number 1 and gas station number 2 had just agreed that they're going to both sell at 25 cents a gallon and didn't try to undercut each other, then they would have made a lot more profit. They would have both made $25 instead of $5. This, of course, is called price fixing and is actually illegal. Two corporations can't come together and say, hey, it's just best for us to both sell at this price because then we'll both make as much money as we can, versus selling at this minimal 21 cent per gallon. This is, of course, a simplified model. It assumes that having a sale of 1 cent is really going to drive all the customers to your gas station instead. If the gas stations are even, say, on the other side of the street from each other, then, northbound and southbound traffic might just take the convenience of going to one over the other, regardless of whether there's a single cent of difference. Nevertheless, this is a good example of showing how, even though a strategy might not be dominated to begin with, once you consider a dominated strategy by an opponent, you might then have different strategies that have been dominated afterwards. The example in this case being that row 2 was not dominated by row 3 until this first column was eliminated. I want to finish with another example of a payoff matrix for a partial conflict game where we successively eliminate dominated strategies in order to find the payoff and the logical solution to the game. So I'm going to look for player 1's strategies first. You could look for player 2's strategies first. It doesn't matter which one you start with. To make it easier to look at, I'm just going to write player 1's outcomes. 4, 2, 1, 2, 1, 1, 3, 5, 2. Now remember, player 1 chooses between rows, so there's 3 possible rows I could choose from. 4, 2, 1, 2, 1, 1, or 3, 5, 2. And is there any row that is always worse than another row in every single outcome? Well, it looks like row 2 is always less than or equal to row 1. So row 2 is dominated by row 1. Player 1's payoffs are always better in row 1 than row 2. So we can go ahead and eliminate row 2. Now between row 2 and row 3, is there anyone that's always better? Well, row 1 is better in the first column, but it's worse in the second column, and it's worse in the third column. So each row has its merits, depending on what our opponent will choose. Now let's go ahead and look at the outcomes for player 2 instead. We have -1, 6, -3, 3, 1, 2, and 1, 4, 7. Now we've already eliminated row 2, so we no longer need to even consider those. Now we can go ahead and look and see, are there any columns that are dominated by any other columns? So what are the columns? We'll have -1, blank, -3, 3, blank, 2, 1, blank, 7. I'm just not even going to write those entries because those have already been eliminated as that row was dominated. Now it looks like column 1 is dominated by column 2. It's actually also dominated by column 3. And so we can eliminate column 1. Notice that if I had still kept that 6 in there, that 6 was actually better than that 1. So it was important that we had first eliminated that row in order to see that we should eliminate this column as well. Are there any other columns that are dominated? Well, no, because here 3 beats 1, but 7 beats 2. Okay, well where do we go from here? Now we just go back to player 1's outcomes again. So we've eliminated row 2 for player 1. Now column 1 has been eliminated. And so now the numbers we're comparing are 2, 1 versus 5, 2. And now, since column 1 has been eliminated, row 3 is always better than row 2, because we no longer need to consider the fact that 4 beats 3 in the first column. So column 1 is dominated by columns 2 and 3. Again, only after row 2 was eliminated. And now row 1 is dominated by row 3. So we can eliminate those entries. And now finally going back to the column, player 2 can either choose between either 7 or... I guess now we could say that column 2 is now dominated by column 3, but I mean, player 2 is just choosing between exactly 2 options, so they're going to choose the higher one. So column 2 gets eliminated, and therefore the final outcome is going to be 2, 7. So, by successively eliminating dominated strategies, we narrowed down on a solution that's logical. If both players think about what the other player will do first and how they might counter that, then 2-7 should be the final outcome of the game. If you actually look, 2, 7 is a Nash equilibrium point. Now why is that? Even without looking at any of the dominated columns, 2 is the highest number in that column for player 1. So player 1 would not like to switch to row 1 or row 2, because 2 is better than that. And 7 is the highest number for player 2 in that row, which means that player 2 would not like to switch columns to column 1 or column 2. And so we've actually found a Nash equilibrium point for this game by doing successive elimination dominated strategies. Okay. In the worksheet, you're going to try to identify dominated strategies and use this method in order to find solutions to the game and or Nash equilibrium points. Good luck and take care.